Oh, right. So what's up? 33, 5, 1. All right, guys, so I got a question on number 33, 5, 1. So let me do a little intro before we do that one. Anything else from homework? I mean, probably a lot of the questions are, what the hell does this mean?
21 on.
Okay, all right. We'll get there. Yeah, good, okay. Yeah. Oh, okay. Oh, 54 is actually, I could talk about that one. I have stuff drawn in my book, which is unfortunate. How do you normally, if I gave you this, let me just show you how this works. And I said, can you estimate what that point right there is? Can somebody estimate what that is? 1.5, 1.5, right? All right. So this is kind of based on that. They give you, they give you like crazy tick marks, and they also give you. Now, what's this here? What do you think this is? Radians, 11. Oh. Right? Because this would be 180 degrees, but it's also what radians? Pi radians. So 3.14. So 3 radians would be just a little bit before there, right? And before I get too far, there's several. Give me the right one? Yes. So it said for t equal to 2.5. So t is like the little variable that represents radians. So if you're trying to do section 5.1 and they say t equals 3, that means 3 radians. T is like the little variable for radians. Is that cool? So at every radian measure, so at t equals 1, there's some terminal point that we started working with yesterday. And we talked about triangles, and I actually took the triangle from the unit circle, but the part we haven't done yet is to put it back. So we talked about 30, 60, 90 triangles, 45, 45, 90 triangles. We talked about what their side lengths would have to be, but I haven't connected that back to the unit circle and the terminal point yet. I haven't done that yet. Right? So we just kind of got into it a little bit last time. Before I go too far here, I want to show you some kind of neat. I want to show you how I can switch these. All right. Well, real quick, just to answer your question while this thing warms up. If I said t equals 2, and they give me all these tick marks, and say for t equal 2, what's the point? You just count over and see what the points are, just like you did with the 1.5, 1.5. It doesn't have to be perfect. You guys understand? So this will be 1, and I think they break it down by tens, if I remember correctly. Yeah, there's 10 little tick marks. So at t equal to 2, you just see how many tick marks do you count over. If it's 8, then that's 0.8. And how many do you count up? Right.
What are you doing? 33?
No, this is 54. The other ones I've got to come back to.
Oh, okay.
The other ones depend on something we haven't done yet. This one, I could give you any day of the week before we even talk about trig and just say, can you tell me, for that one marked 2, can you tell me what the point would be on the circle? Well, you just count over in the x and you count up with the y, and that's how you figure out what the point is. Always. They just have to give you good enough tick marks to get a better estimation.
So you have to go halfway. Now I see the problem. You have to go halfway between 2 and 3, and then do ticks to find that point.
Exactly.
Okay.
I like it. So halfway between 2 and 3, there's a couple of estimation points. Your answer then to be perfect. It's got to make sense. Now tell me this. If this is 0.8, what will actually my point be? What's the first piece of the point going to be? If this is 0.8 here, if this is like 0.8, What's my point look like so far? Negative 0.8. Good, because it's back here. All right. So trig functions that relate to the x-axis are going to be negative here. Right? Here and here. Trig functions that relate to the y-axis are going to be negative here and here.
The columns go 1, 2, 3, 4, right?
No. 1, 2, 3, 4. Counterclockwise. Right? They did that just to be dicks. I wasn't around. That's my best guess.
Would it be easier to do it clockwise?
Yes, it would. No. Don't remember my password. This isn't exactly the one I had found before, but it has some of the stuff I wanted to show you, sir. I don't know if you remember, I tried to do this on the board. I tried to talk about how this would work. But I just want to show you a little GIF that will show you. Come on. Load up. Oh, I love this. Let's try Chrome. That's what I should have done in the first place.
A quick question about those tick marks. You start from 0, correct? So you don't start from, you start from 0, 0.
Yep. All right, Chrome. You just not want to work today? Technology. All right, let's see if this is like backwards today here. If Explorer works better.
Do you think student athletes should get paid? Could you have ever been? I know you were just in Vegas and we were talking about the March Madness thing. I was just buying time.
Oh, I see. It's like the little. Let me give you a topic.
Yeah,
No, Saturday Night Live. You remember that, Mike Myers, back in the day before he made Guru and fell out. I don't know, man. I think they're making so much damn money, and those people are the ones doing the work.
Right.
Scheisse. So they got to alter the rules. So they
$1
actually
billion
get
this month.
It's insane. Or they just decrease the damn ticket prices. Don't make so much freaking money, and let people actually go and watch the game that can afford $4.
Those coaches make like
Anyway.
$4 million a year.
Right.
The students get paid.
Nick Saban makes like $8 million.
I don't know. Computers. All right. So while this computer's deciding whether or not it's going to work, you guys just stay with me now.
Well, I mean, they could literally get banned.
So a real quick reminder of what we did the other day. We had a 60, 60, 60, right, equilateral triangle. We dropped that bad boy down. We said it came from the unit circle. So it was 1 all the way around. And so this would be 1/2. And then we did Pythagorean theorem. We figured out this would be root 3 over 2. What's this angle here in the right triangle? It's got to be 30, 11. So notice what that means then. Let me make the connection between this and the unit circle now, and the terminal point that the book talks about, the T. Right? If I am at a 30-degree angle, which is what in radians? What do you divide 180 by to make 30? See, that's 5 or 6 then. You can understand how to think about it very quickly. Right? So that's 5 or 6. So before I go back there, let me just finish talking about this. If I'm at 30 degrees then, I could draw that triangle because the point will be the x piece, comma, y piece of that triangle. Are you with me? That's the connection between the terminal point and the triangles that we were drawing last time. So I really didn't fully make this connection yet, but that the x piece here, is it going to be longer or shorter than the y piece? And don't even just base it off of how I drew this, but think about it. Where's the bigger angle here in this triangle? I mean, the hypotenuse I know is 90, but this would be how many degrees? So which side should be the longest? The x side, right? And we know across from the 60, we proved the other day that across from the 60 should be root 3 over 2 if the hypotenuse is 1. Let me say that again. We proved yesterday that if the hypotenuse is 1, across from the 60 is going to be root 3 over 2. And across from the 30 is going to be 1/2. And why does that make sense? Which one of these is bigger? Root 3 divided by 2 or 1 divided by 2?
Root 3 divided by 2.
Yeah, root 3 is bigger than 1, so root 3 divided by 2 is bigger than 1/2, right? So what this means about this terminal point is the x piece is going to be root 3 over 2, and the y piece is going to be 1/2 because it was a 30-degree angle. So that's the connection. Is everybody cool with this that we did the other day? So you notice if I just turn this way, that's exactly what I have there. So this side would be root 3 over 2. Bam! This much is root 3 over 2. This much is 1/2. So the point is root 3 over 2, 1/2, because that's the x piece, comma y piece. Right? How you put points together. So, yes, sir?
That's if the hypotenuse is 1.
And the beautiful thing I want you to realize, what trig does is you might start to go, well, not all triangles have a hypotenuse of 1, Jeff. But trig functions are all about ratios between sides. So I appreciate you asked that question. Let me real quick address it very quick. So if I draw 30, 60, 90, if that's 1, this is going to be what? 1/2. And this is root 3 over 2. So what's the ratio between, let's say, the x piece and the hypotenuse? What's the ratio between the x piece and the hypotenuse? What's that ratio? Root 3 over 2 divided by 1. You guys with me? That's what I mean by ratio. Ratio of the sides. Root 3 over 2 divided by 1 is root 3 over 2. Now, if this triangle, well, you're like, all right, Jeff, not every triangle has a 1 hypotenuse. What if it had a 12 hypotenuse? Right? So pretend like this is 12 times bigger. It's way far back.
The ratio is still the same.
The ratio has to stay the same. Well, let's prove it. If this is 12, it's 12 times as big, so all the sides have to be. So this is not 1/2 anymore, it's 6. And this is not root 3 over 2 anymore, it's 12 times this, so 6 root 3. What's the ratio of the x side to the hypotenuse? It'll be 6 root 3 over 12, which is root 3 over freaking 2. That's why you can have a single function that you plug a 30 degrees into. And if it's the function that relates the x piece to the hypotenuse, it'll always be root 3 over 2. Because it's ratios, it'll always have to reduce. That's the beauty of trig. It says, look at the unit circle. And everybody's like, not every unit has a circle has a one. No, screw it. That's the lowest common, that's in lowest terms. So the minute you know all these, you know everything. I don't care how big the damn triangle gets. It's going to reduce to that same ratio, 11 for a 30-degree triangle. So what if it was at 60 instead? What would that terminal point be? Do we have to do a lot of work? We shouldn't have to do much work at all. It's the same damn triangle. I just have the bigger angle here now. So which one's going to be bigger, the x or the y? The y. So instead of root 3 over 2, 1/2, it's 1/2 root 3 over 2. It's the same damn triangle. So the sides, the x side and the y side, are now the y side and the x side. It's the same freaking triangle. So it's just, right? Or whatever sound effect you want. And then what if I go back here? What if there's a triangle that this angle here is 30? Yeah, that'll be the same as that, except what's negative now? X. So that's the terminal point there. So what does that really, and you can see I can just do that in every damn quadrant, and then you just have to figure out here, if it was here, what's true about both x and y are negative. So since I know this, I can just plug negatives on both. So where's the only quadrant that we actually have to memorize anything? The first quadrant, because then you can just plug the right negatives in the right place for everybody else. So you have 1/4 as much to memorize as you might have feared. Right? Or some of you guys are like, memorize? Yes. Memorize. Hell yes. Yes. So it's sort of like memorizing your multiplication tables. Doing any trig requires you to know some basic angle outputs. Now, we're not going to memorize for 31 degrees and for 37.89 degrees. We're going to memorize for 30, 60, 90, 45, 0, and, well, I already said 90. Right. everything in there. That's the main anchor point angles.
I wasn't here on Thursday, but I've actually got a trick for this that I picked up because it repeats. It's always the same thing. It's 1, 2, 3, 3, 2, 1. Everything over 2, and then the.
I'll show you an even better thing. I'll show you.
a better one?
Well, it's related to that, but it's more direct. Well, yeah. I like that.
You know where I'm going.
Yeah. All right, let me see if it works here. I at least want to show you this one thing.
Here's the Vulcan. What's that
I didn't catch him. It's just some teacher somewhere.
This is
All right. There we go. Now watch. It's kind of cool. Here's a representation, if it'll actually load, of. There we go. Here's pi. Well, let's do it again. So see, it's all. Yay! Well, that's interesting. So that's just like taking the circle and laying it out. And it shouldn't go all the way around. That's a little troublesome, but we'll go past that. This is the one. This is the one I was trying to do. There's the radius, and it makes a circle. Now you pick the radius up, and you curve it, and there's 1 radian. Cool. And then 2 radians, just like the picture I had up here earlier. 3 radians. Add a little bit, make it pi. Do it. Yay. All right. Anyway, and then 2 pi's all the way around, and I think that's where it ends. Shoop! Yep. Just a little bit beyond this, I'm not going to show you that one, but now that I've got this thing finally loaded, this guy? Oh, who is that? That's, he teaches Spanish or history. Shit. That's really good job. He teaches one of those things. Alright, so I'll let that stay there for a second. Alright, so let's continue really solidifying this relationship. The more you know these terminal points, the easier it's going to be to memorize the actual functions. So the trig function that relates the x piece to the hypotenuse at 30 degrees would be root 3 over 2. Let me say that again. The trig function that relates the x piece to the hypotenuse at 30 degrees or pi over 6 will be root 3 over 2. The trig function that relates the y piece to the hypotenuse will be 1/2 at 30 degrees. So the trig piece that relates the x piece to the y piece will be root 3 over 2 divided by it will be root 3 at 30 degrees, and so forth. That's coming up later. So remember, every single trig function is just a ratio of sides from a triangle from the unit circle. Ooh. Right. Very simple little thing. And then we just do like crazy amounts of shit with it. Okay. So let's further solidify this thing here. So what about at 45 degrees? What did we figure out last time about 45 degrees? Who remembers what we did there?
A quarter pi.
Good, I like it. So in radians, this would be pi over 4 radians. Who remembers what the sides were? We looked at a 45. Yeah, so this will be this terminal point.
Is square root of 2 divided by 2.
Yeah, is root 2 over 2. Root 2 over 2. Cool. Oops, I got this in the wrong place. This one. 1. So this would be the 90. This would be 45. 45. And so we used Pythagorean theorem last time we figured out what these sides were. Is everybody with me? All right, cool. So it makes sense that at 45 degrees, the trig function that relates the x piece to the hypotenuse and the trig function that relates the y piece to the hypotenuse will actually have the same exact value, because at 45 degrees is exactly halfway. So it starts off at 0, it starts off at nothing but x, right? So the trig function that talks about the y piece should be 0 at 0 degrees, because there is no freaking y piece. The minute it lifts off the x-axis, now there's a y piece. And where does the y piece become maximum? 90 degrees, right? Cool. So this at 90, the trig function that talks about, or pi over 2, rad, that talks about the y piece should be most, and then one that talks about the x piece should be 0, because there's no x piece here. I like it. I like it. Okay, cool. So now let's finally, I've been saying trig functions drive me crazy. I want to say the actual functions. So let's talk about those. And we'll put these all together. Before I get too far though, there is something I want to talk about more formally here. This idea of, notice that we keep getting these angles here. But let me ask you this. If I only have to memorize stuff in the first quadrant, because then I can just throw signs in the right place based on which quadrant I'm in. Does everybody get that basic idea? If I know the values here, they're all the same freaking triangles. It's just facing the other way. So like x is negative there. It's the same values except the x piece is negative, for example. Right? Here they're both negative. So forth. That means that I want, if I'm given some angle, like let's start off with degrees. For angle 210 degrees, what would I actually want to think about from quadrant 1 that relates to that?
30 degrees.
30 degrees. Now, why did you say that?
B subtract 180.
I love it, because you wanted the angle that I want to use is the angle how far away I am from the x-axis. So 210, any given angle is going to go from the 0 point, right? It's going to start at 0 and go all the way to 210 degrees, right? Well, you don't want to do that, I'm going to hurt myself. So all the way 210 degrees. When we want to figure out the terminal point, we just want to consider the quadrant 1 angle, which would be 30 degrees for the triangle. Do you guys see how that's not a big deal? If I drew a triangle there, 180 of those degrees weren't worth shit for my triangle. I just want to know how far past the x-axis is going to go. That's what the angle actually is in that triangle. Does that make sense? This is the idea of finding a reference angle. Right? 210 is the actual angle. The reference angle for this would be 30 degrees. And that's why we based it off of the values at 30 degrees. So for angle 210, the reference angle would be 30 degrees. Good. That would be 7 pi over 6. And a real quick way to say that, you're going to start to realize pi over 6 is how many degrees? 30. You've got to love that, because pi over 3 is... 3 and 6, of course, go together because they make 18. It's based off of 180. Kick-ass. So pi over 3 is 60. Pi over 6 is 30. Pi over 4 is a dude in the middle. 45, right? This stuff becomes a little bit easier than you might have thought. So when I look at 7 pi over 6, I know that pi is where? 180. Yeah, pi is there. So how much past pi did I go in radians? 1/6. Not degrees, radians. 30. So if I'm talking about 7 pi over 6, how much is this actually?
1/6 of a pi.
Yeah, pi over 6. I want 1/6 of a pi over, right? If I got 7/6 of a pi, I could eat a whole pie, get sick, and I'd still have 1/6 of a pie to look at and get sick again. One more pie. Right? What a beautiful image. Yes?
So, is one way you got the number, you can count how many 30 degrees are all the way over. So it's 210 degrees. So it's 30, 60, 90, 120, 150, 180, 210. That's why it's 7.
Yeah, it's 7 30 degrees. And every 30 degrees is pi over 6. Beautiful. I love it. That's that's fine. Nothing wrong with that at all. Yeah.
Couldn't you do a similar thing counting by 45 degree angles if it was like 3 pi over 4?
If it's over 4, it's related to pi over 4, which is 45. Exactly. So you can extend that idea. I love it. Kick ass. And that whole thing is just whatever makes the most sense to you. At this level, you should be comfortable playing with numbers in that way. You can figure out your own good way to get there. Right? So let me ask you a few things here. Find the reference angle and the terminal point for each of these. You ready? All right. So 2 pi over 3. These are all radians. If they don't have a little degree symbol, they must be radians. What you got, Jeff?
off in radians and bring it back to radians.
There's nothing wrong with right now converting this to degrees. To think about it, because we're just getting used to radians, but always try to bring it back to radians at the end for the reference angle. I've desperately got to get you guys used to radians, so you just
You
know.
wanted the reference angle for this?
Yes.
Oh, I misunderstood. I'm sorry.
So for this guy, if we draw a little picture, 2 pi over 3 is just a little bit, is like a third of a pi less than a full pi. Is that, you guys with me? So it'll be over here somewhere. So a third of a pi less. All right. And what's the reference angle in radians? I mean, I basically just gave it away. Yeah, all right, pi over 3 radians, right? So the funny thing is, in order to draw it, you actually have to think about it the way you have to think about it to find the reference angle. How far away from the x-axis is it so I can draw it in the right place? So it's a third of a pi from the x-axis, which means the reference angle is a third of a pi. That's how far away it is from the x-axis. So the reference angle is the closest degree measure to the x-axis. Period. Does that make sense? Because I could reference this to the x-axis back here, but that would just be 2 pi over 3. The reference angle is the closest it gets to the x-axis, how far away it is there from there, in radians or degrees. So if we did this in degrees, 2 pi over 3 is how many degrees?
120.
Good, 120. And how far away is that from 180? 60, which in radians is pi over 3. Kids. And why does it make sense? I really want you to understand. Why does it make sense that the reference angle is where it is? Because if I try to draw this triangle, don't I have to know this degree? This will that measure? Right? That's why we call reference angle that. Because then it makes us only have to memorize stuff in the first quadrant. It's awesome. Let it be awesome. Now what's the terminal point for this? I love it. And think about this. Here's how I think about this. If I am at a reference angle of 60, that means the y piece is bigger than the x piece. Right? I'm closer to the y-axis, so the y piece is bigger. And if you just remember, for 60, 36, 90, it's 1/2 and root 3 over 2. You know where to put those. The y piece is bigger, so root 3 over 2 goes there. 1/2 is there, and then you attack it with, I'm in quadrant 2, so what's negative?
Yes.
Kick ass. Let me stop there for a minute. And never forget what's true about these together, what they always have to do together. Where do they come from? They're sitting where? Where are they sitting? What do they sit on? What do they sit on? The unit circle. So what do these have to always do? What's the definition of the unit circle mathematically? What's the functional relation? Beautiful. So that squared plus that squared must always be 1. And that, of course, is true here. If you try it, it'll work. You get 1/4 plus 3/4 is 4/4, which is 1. Square root of 1 is 1. Yeah, yes. Pythagorean theorem has got to always work on these. All right, cool. What about this dude? Where the hell am I? I'm just short of what?
2 pi.
Yeah, and how do you know that? 2 pi would be what pi over 6? 12 pi over 6. I'm trying to force you to think radians. If you make it degrees, we're so used to degrees already. So part of this course is trying to get you completely used to radians. I know you guys know degrees. You should. So I'm pi over 6 short of the x-axis, right? So I kind of know how to draw this thing. I'm pi over 6 short. Just 1/6 of a pi away. So that's my reference angle. So it's kind of silly. In order to draw it, that's why I always make you draw it. If I force you to draw it, you sort of accidentally stumble onto the reference angle, which is nice. If you try to think of the reference angle by yourself, it's a little bit harder. 1/6 of a pi away, that means the reference angle is pi over 6. So what would this point look like? Which one's bigger now, the y piece or the x piece?
X.
Because I'm closer to the x-axis, right? Kick ass. So the x piece should be root 3 over 2. I like it. It's positive. Negative 1/2. Kick ass. And again, where are those numbers coming from? We proved that a 30, 60, 90 triangle will always have these. And 1 is kind of in the background here, right? 1 is what these two combined squared y's to create. Are you guys with me? So I know for a 30, 60, if I have any of that kind of reference angle, I know these are the numbers I'm using. Just where do I put them and which one's negative or positive depends on where the hell I am. Maybe. All right, so I wanted to give you one that wasn't 30, 60, 90, just so we don't get too stuck in that trap. And by the way, you should be able to tell me, obviously, this is quadrant
2.
maybe not so obviously. Quadrant 2. My bad. So this is this point is in quadrant 2. This point is in quadrant 4, and this point is going to be in
3.
Good, because it's how much past pi? 1/4 of a pi past pi. All right. So that means my reference angle is exactly that. It's 1/4 of a pi. Cool. I like it. So here the x and y pieces are
Negative.
I like it. And they are also equal, because it's exactly in the middle. So the y starts at nothing and it grows to 1, and the x starts at everything and it shrinks to 0. So right in the middle, they're going to be passing each other. They're going to be right at the same location. So that's going to be, the terminal point here will be, yeah, they're both negative, and it's root 2 over 2. Kicking the acid.
So if it's a 45-degree angle, it's always a square root of 2 over 2. Square root of 2 over 2. That's always what it's going to be.
Always. It's silly. It's always what the ratios of the sides will reduce to, right? Because like the hypotenuse is going to get bigger, but all the sides will get equally bigger. So when I take a ratio, it'll shrink to the same thing. Cool. Oh, somebody keeps screwing this poor thing up. Poor little dude. Oh, wait, Jeff. Just don't kill yourself. All right.
Oh, crap.
Oh.
That's the other one. That looks like a 30% degree angle. Yeah.
Just missing one of those. It doesn't have one.
Oh, wow. So you really screwed this thing up.
The board is in quadrant.
What the hell is happening here?
I think it's supposed to screw in it, but it's.
That's all right. That's the appendix. Or doesn't really need it. I'm like, and then you. It's like, all right. That's a little more exciting than a board should be. All right. What was I going to do? Oh. Before I can give you this handout, which is a really kind of nice handout to have, I want to introduce finally these trig functions. All right, so we keep talking about talking about. So I'm going to talk about them in terms of triangles, but just never forget that the triangles we're looking at could come from a circle. Maybe not a unit circle, because I could draw a triangle with a hypotenuse of 1100. That's not the unit circle, but they're the same kind of triangles we were just looking at from the unit circle. You guys with me? And even if they're huge, the side ratios will reduce down to the numbers we're used to. Right? Those numbers. Cool. How are we doing so far? All right. So here we go. Theta is the preferred variable for angles. X and Y are variables for real numbers. Right? N is a variable for a natural number. Theta is a variable for angles. And we also use capital letters for angles too, sometimes. We get tired of drawing Greek letters. So sine of theta, which looks like sine theta, which is not sin. So sine theta is defined to be the ratio of the x side to the hypotenuse. Jeff, start off correctly. The y side. We were just talking about x forever, and I got stuck there. So sine likes y. Let me try to really make this, because I wrote the damn wrong letter in the first one. Sine likes y. Sine is always the ratio of the y side of the triangle to that hypotenuse. How we doing so far? So if you give me, if I said, let's investigate this for a second. If I said, what's sine of 30 degrees? Now you got to think a little bit, because this is not an automatic. It's not like me saying, what's the square root of 9? You don't have to think at all, because we're used to it. But what's sine of 30? At 30 degrees, will the y piece be the bigger piece?
No.
And sine likes y. So the sine should be the smaller piece, which is 1/2. Kick ass. And in fact, before I introduce any more trig functions, let me kind of piggyback off of Morgan. I like that. I've never heard a student kind of give me what I like to do. Because you're really close to what I like to do. You guys ready? This is kind of kick ass if you let it. Right? So sine, here's what sine does. This is all about sine. At 0 degrees, or 0 radians. Let's do this all in radians. Fine. At 0 radians, the sine of 0. What do you think? Sine likes y at 0 degrees. How much y is there? None. It's all x, right? Cool. So sine of 0 would be 0. And in fact, well, let's see. So at 30 degrees, we just figured out it's 1/2. It grows from 0 to 1/2. So when at 0, there's no y. At 30 degrees, there is some y. And then at 45 degrees, there's a little more y, isn't there? And of course, sine of 45 degrees is going to be beautiful. Now watch this. Let me go a step back. Don't let this interfere with your... Well, let me see. Let me see if you guys like this. If you like it, cool. If you don't, I don't care. You can figure out whatever memorization method you want. But watch this. Isn't that the same thing? And isn't this the same thing as 0? So what does sine do? Root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2. And sine of 90 is root 4 over 2, which is 1. Yeah, root 4 is 2 divided by 2 is 1. That's a kick. I mean, come on. I can't do more for you. So I kind of made this up myself, and now I hear it every now and again. So I'm like, cool, this is getting out there. Because this is one of the... I've seen all this weird shit about counting on the knuckles and weird shit. I don't know if anybody ever has that other stuff that they do. To me, this is awesome. Cosine... Oh, shit. Well, the one that talks about x, which is called cosine, we just do all this in reverse. Because it starts biggest, and then it shrinks. Right? How are we doing? You doing okay? Can't beat this. I want you to understand it. You don't understand it. You don't. But it's all right. So cosine seems to be a good name for it. It's the partner of sine. So cosine of theta, which is cosine theta. That's the one that's x over that hypotenuse. That's the ratio. So no matter how big your triangle gets, cosine of 30 will always have the same value because the sides would reduce. That's why trig is so powerful. So what would cosine of 30 be? Yeah, because it's really close to the x-axis. That's where it's the biggest. So at 30 degrees, it's going to be the bigger option, root 3 over 2. That's actually exactly how I have it memorized. At 30, cosine's like x. It's not very far from the x. It's bigger. At 60, it's really far away from the x-axis, closer to the y-axis. Cosine's going to be smaller because it doesn't like it up there. It likes down here. It doesn't like it up there. You're like, oh shit. So cosine 30, root 3 over 2. And it's going to do the exact opposite of what I said up here. It's going to do, starts at 1, because at 0 degrees, the radius is 1 on the inner circle, it's all x. Right? And then it's going to go down to root 3 over 2, root 2 over 2, root 1 over 2, 0. So it does the exact opposite of what that does. How are we doing so far? Was that a good explosion? Okay. I never know. It could be a bad explosion, you know. So 1, root 3 over 2, root 2 over 2, root 1 over 2, which is 1/2, and 0. So this is root 4 over 2, remember? Okay, there you go. I like to show that. I myself don't really use that, but it's good to see that. That's what's happening. The x side is getting less and less. Every triangle here, the x side starts off huge, and now once I'm here, the x side is way less than it used to be. In fact, it's exactly 1/2 as big as it used to be. And of course, once you get here, there's no freaking x at all. Oh shit! All right. So, what other ratio? Oh, before we get too far, let's go ahead and play with these a little bit. If I give you a triangle like this, let's talk about just straight up triangles. Because these triangles actually don't even have to... Oh, let me show you. Let me see what you guys think. Now that you know what sine and cosine are defined to be, if I give you, I don't care what triangle I give you, it doesn't even have to have a nice angle measure. What is it, Jeff? 3, 5. Some of you guys got to be careful. You might know too much, just enough to be dangerous to yourself. It's not a 3, 4, 5 triangle here, right? It doesn't have to be 3, 4, 5. It's 3, 5 shit. So if I ask you, what is the sine? Let me give this a name. Let me call this A, just to be different. We use capital letters for angles. You've seen that in geometry, hopefully. But we also use theta sometimes. So what's sine of A? What do I have to know to figure out sine of A? What's sine of A defined to be? I hear some of that SOHCAHTOA shit out there. I'll tell you in a minute. If you know SOHCAHTOA, if you have no idea what SOHCAHTOA is, you're like, soak your toe? If you know it, you can use it, that's fine, but I desperately wish they would never teach that. Now, some of you guys automatically hate me a little more for saying that because you're like, it makes it so easy. But it only takes you so far. How far do you have to go with trig? This far. How far does SOHCAHTOA get you? This far. But if you learn from the beginning, trust me, this is a huge deal for me. If you learn from the beginning that sine likes y, cosine likes x, you go all the frickin' way. It's beautiful. If you just remember that. When you take physics, you got to have a vector of force and you got to break it down to the x and y piece. Cosine is x, sine is y, bam. No SOHCAHTOA shit. There's not even a triangle there. You guys kind of with me? A little bit? So if you know SOHCAHTOA, I'm not going to take it away from you. Like if you know FOIL, I wouldn't take it away from you. But FOIL's just freaking repeated distribution. Why do you need FOIL? It's bullshit. SOHCAHTOA, fine. Have it. But if you don't know it, don't even look it up. Don't even think about it. Screw it. So for sine, sine is defined to be the y piece over the hypotenuse. And of course, what do I not know? And of course, how do I get it? Yeah. So far, in fact, through all of chapter 5 and most of 6, we'll have to be using right triangles. Right? Everything we've done so far is based on right triangles. At the end of 6, we're going to expand that sines and cosines to include things that aren't right triangles. And that's when I get to the law of sines and the law of cosines and kick ass. Where we go Pythagorean theorem is just a specific situation. There's a more general rule than the Pythagorean theorem that we all know. That's in our future. So the y piece I know. What's the hypotenuse going to be?
X.
Let's call it h. And how do I... It doesn't matter what you call it. You can call it x if you want to. But I normally stay with that's x and that's y. How do I get this, of course? What? So h will be the square root of 34. Good, so what's the sine? Yes, and you can simplify that a little. You can rationalize the denominator. I like that. You can rationalize the denominator. So make that's got to be a part of your process. This is not good. This is sort of like saying the answer is 6/8. Like, you know better than that. So the same thing. You got to take one more step. Simplify the denominator. Rationalize that bad boy. You guys with me? So is this angle an angle that we know well? No, this is not root 3 over 2. This is not root 2. This is not anything we know. So the angle is just not 30, 60, 45. It's not one of those. Ooh, big deal. Right? Later we'll actually learn how to figure out what the angle is. And real quick, while I'm talking about that, if I said natural log of A equals 3 root 34 over 34. How would you figure out what A is? You do the inverse of ln, right? So how do you figure out what A is here? Inverse of sine. So at some point we have to actually learn what the hell the inverse of the sine function is. No, that's reciprocal of the sine. Yeah, those are different. Yeah, that's equal. What's cosine of A going to be? So it's defined to be x over h. I like it.
5 to the square root of 34 over 39.
Good. So yeah, we can kind of skip ahead a little bit and go, it's the same thing, I just have a 5 instead of a 3. Is that cool? What's one thing you can do to check your work here? And remember, this is the y piece, and this is the x piece, and if you square them and add them, what are they supposed to do? So here's a real cool thing. This is a little bit ahead, but I want you to just realize how simple this comes. Sine is the y piece. Cosine is the x piece. When you square this, and you square this, you add up to 1. So sine squared of an angle plus cosine squared of an angle has to be 1. Hey, there's our first trig identity. Holy shit. That's a 2, by the way. It's been through a few things. All right. Normally I don't just introduce this till later, but it's a very simple idea. I know the y squared plus the x squared has got to be 1 because it's based on the unit circle. Well, sine is the y piece. Cosine is the x piece. And yes?
So that would be your terminal point?
The terminal point would be, well, yeah, good question. What would the terminal point be here? What's the x piece? Yeah, 5 root 34. Yeah. Around 3 root 3. Alright. I'm tired. Yeah, that's the y, the x piece, that's the y piece. So all the terminal point work, I'm glad you brought that up. All the terminal point work you've done, and it really relates to this, that was easy because of all the terminal work we've done. Terminal point work. Right? Sine of 30 is the y piece of the terminal point at 30 degrees. Does that make sense what I just said? That's all. All right. Hopefully. Okay. All right. Whew. So let me finish out all the trig functions, then I can finally give you this handout that I've had since last time. There are 6 total trig functions that we'll talk about anyway. Yes?
Just real quick. So when you plug that in, would you be squaring the whole sine of A? Just because
Yeah, you would square this whole thing, or you could square it like this, it'd be a little easier. So if we check this, it would be 3 over root 34 squared plus 5 over root 34 squared. Is that cool? I'm just doing the unrationalized, because I'm going to square it anyway. So I'm going to kill the radical that way. And that's going to be what? It's going to be 9 over 34 plus 25 over 34 is 34 over 34. Some of you guys might realize, well, 34 came from us doing this kind of thing, so of course it's going to kind of come back together. But it's still nice to see that it works. And if you got time, then you can kind of check your work. Make sure that things make sense. Okay. So the last few trig functions here. Kick ass, you've got time. So far we got sine, cosine, tangent. Yeah, this is the tangent. The tangent's going to be sine over cosine. Is one way to define it. And of course, if you do that, the h's cancel, you get y over x. So when you get to calculus, you talk about a tangent line, and students are always like, does that relate to tangent that we learn in trig? And exactly, because what is the change in y over the change in x? That is the slope. So the tangent is somehow related to the slope, because it's y over x. Yeah, so you'll investigate that more when you get to calculus. It might come up again here later, I can't remember. Everybody's cool so far? This is just definitions. We're creating functions that relate to certain ratios of sides of triangles. You could do this all day long if you want. You could make functions that do whatever the hell you want them to do. But these are very useful functions.
Why do you flip it?
Flip what?
Sine A cos.
Flip it. How do you mean flip it?
Like, is it cosine of A is Y or something?
cosine of A is the x piece.
X piece. Cosine is the X piece.
Okay.
Sine's the Y piece. Cool. Get that really stuck in the head. Cosine likes X. Sine likes Y. Cool. All right. And then there's these. So that's actually, to tell you honestly, those are the three main trig functions, and even one of them is based off of those two. The remaining three trig functions are just all of these reciprocating. So don't worry about this quite yet. But the one that goes with sine is called cosecant. Cosecant. S goes with C. Right. And that's going to be the reciprocal of this. So this is just going to be H over Y. And the one that goes with cosine is going to be secant. So that's going to be H over X. That's craziness. And the one that goes with tangent is the one that actually makes the most sense. Right now, anyway, you'll see why this is defined the way it is later. This is called the cotangent. And that'll be X over Y. Okay. You stop there for a second. So on one level, this is remarkably, awesomely simple so far. It actually never changes from this basic definition of what these things are, but the way you can use them just doesn't seem to end. And then you start thinking this is more and more complicated because we're using them for more and more complicated reasons, but they always come back to being ratios of sides of triangles. That's all they can ever be. So about 2 weeks from now, or 3 weeks maybe, got to include spring break, thank God it's coming. We'll be like trying to remember, oh yeah, they're just ratios of sides of triangles, even though we've done all this shit with them. Okay. So let me finally give you two things. You give me this. This is loaded with stuff. I still want you to have it. The bottom is getting a little bit ahead of us. It's actually graphing sine and cosine. Don't worry about the bottom too much yet. The top, you'll see something very useful that you can use for homework, but not for tests. Don't get too excited.
Awesome.
So really quickly, I want to show you this animation. This is a little bit ahead of us, but just because it happens to be down here. See, the middle one is just going around a circle, right? So what's happening is, this is the cosine, this is the x piece. So the cosine just traces out what x does. And what does x do? Starts at 1, goes to 0, goes to -1, goes to 0, goes back to 1. So it's going to 1, 0, -1, 0, 1, 0, -1. And this is just capturing as it's growing and shrinking and growing and shrinking. You guys understand? And the sign looks the same, they're just offset. Because sine is biggest here. So everywhere cosine is 0, sine is going to be 1 or -1. Does that make sense? So they're the exact same. These are the things you see on oscilloscopes in the background of some mad scientist movie or something. Right? You got this, and then over here you got the, or if anybody works with sound, and you actually see this, does anybody work with sound in any way? Do you use oscilloscopes and you turn the gain down in case it gets all flat on the top and shit like that? Okay. Yes, good. So you kind of have an advantage a little bit, because if you work with sound at all, you're so used to this kind of thing, and then adding them together and trying to cancel them out and whatever. I love it. My little brother works with sound, even though he has only one ear. He was born with one functioning ear, but he's like this monster sound engineer and stuff. So I'm always, he can hear something and play it immediately, whereas the rest of the family has zero musical ability. So he just got it all. It's fine. Anyway, so I love that kind of 3D thing, but don't freak out. We're not going to sell you doing a lot of 3D stuff. And then here's another one, it's even a little better, I think. So you see how when cosine is the biggest, right, there, sine is the smallest, and so forth? Alright, maybe. So cosine is tracing out what the x piece is doing, and sine is tracing out what the y piece is doing. I think they got the picture a little bit off, but it's close. Oh yeah, that's getting a little ahead. Alright, we'll go there too yet. Alright, so, before I have you work on this, the only thing you have to be careful about with these, this is the only thing. Remember, SOHCAHTOA, this far. X, Y, sine, cosine, all the way. You understand all the shit you got to do with trig if you base it off of that. The only advantage SOHCAHTOA has is it doesn't care how the angle is oriented. So I'll show you what I mean. So if I'm talking about a triangle like this, and I want to know about angle B, notice how it's not in the base. So this is not my x piece. Because when I do the unit circle, where's my angles that we always talk about? Where are they? They're always in the base of the triangle, right? You guys see what I mean? They're always here. So all I do is, if this is a 7, let's just make it 3, 4, 5. Just make it quick. I'm going to call this x and I'm going to call this y, because if I turn this, this is the x piece and this is the y piece. And then I can just go ahead and do this. SOHCAHTOA, I'm trying not to say too much about SOHCAHTOA, but SOHCAHTOA is not just a camp you can go to and hate, but it's also sine. So sine of this would be what? What would the sine of B be? The y piece over the hypotenuse, right? So means sine is opposite over hypotenuse. Opposite over hypotenuse. Cool? And I desperately want you to, if you've never seen SOHCAHTOA before, don't even use it. You've got to trust me on this.
That's what you don't want to say.
And this is where people just say, you're just being mean, Jeff, because this actually does kind of make it easier, but it doesn't get you anywhere near as far with trig. It's only useful to a certain point. Everything you got to do with trig after this class is going to involve you understanding that sine likes y, cosine likes x, and if you learn SOHCAHTOA, you're screwed. So I teach Calc 2. I see students who did SOHCAHTOA and only SOHCAHTOA, and they suck toes. They just can't. So I got to kind of reteach them a little bit and say, no, you got to look at it like this, and then everything's like, oh, that makes more sense.
So if we see a triangle like that, it's pretty much split it.
Yes. Make sure the angle's in the base, and then this stuff works beautifully. So here, I want you guys to do this real quick. You're all pack it up anytime ago.
If we can do 5-1, can we do 6-1?
There's two ideas in 6-1 that we haven't talked about yet. But they're formulas that they give in the section. You can just use them. And I think next time I'm going to prove the formulas. But today I wanted to get to sine and cosine stuff for sure. You should be able to do most of 6-1, but like I said, there are some formulas that they derive, and then they want you to use them. To be honest, after today's lecture, you could do 5-2. So call me over if you need some help. The last triangle doesn't have a question mark, but there's no trick there. You still have to do the same thing. Oh, and real quick, I forgot to say this earlier, but sometimes, like on the paper there, instead of H for hypotenuse, you'll see R for radius. Because remember, that's exactly where it came from, the radius of the inner circle. So in these definitions, instead of H, you see R. It means the same thing.